So here's my Breitenberg biological cybernetics update. That is a vehicle, a multi-sensory vehicle. So you take a few random sensors, connect them in random ways to the motors here. And I made a little bit of an environment now with sort of here random temperature bubbles. This is random. I call it oxygen, and this I call food or something. So basically, he has smell detectors for food now, and smell for oxygen, and he has basically a ray detector for these light sources here. So they have slightly different sensor behavior. So the light is stronger depending on how you rotate it, but the food is diffuse. So you get a little bit of different things. And yeah, so it's I would say that's what Breitenberg was imagining. That's what you would be able to build. Now the next thing would be that you make this, of course, somehow with some evolutionary plan. It would be vehicle 6, that there would be some genetics here that would determine this, and then they would survive or something. Or you would need to think about how to model it or something. The easiest would be to play the game over and over with vehicles, of course, or something. But yeah, so I thought it was. No, I have another one where I spawn 3 at the same time. Or maybe it's too much, I'm not sure. But yeah, you can click on them, and they're sort of different. They're different guys. This one doesn't have so many sensors as the other ones, or something. Yeah. It's less hectic, I guess. Yeah, I'm gonna go back to a single one. Yeah, that one is peaceful. It doesn't have a sensor for this cold thing, I guess. Does it? Yeah, it moves away from cold, I think. Yeah, so you see down here that this is the cold sensor. So yeah, when you click on him, like it's like in Dungeon Keeper, you click on a guy and you sort of get his internals. Yeah, and I love this, how these things are rotating this way, and I was sort of imagining, hey, if you take a snapshot here, it's a little bit as if you take a snapshot of his mental state. These are the sensors, and they're sort of like a kaleidoscope of pattern together that basically say what you're going to do here, or something, a little bit. And here you can also click and see what these things are doing. So yeah, I see from the colors. Yeah, this one is blue. I think this means that's a cold. Yeah. So he is going, and he actually likes cold now. I mean, he's kind of slow when it's cold. Yeah, and he's going intense when there's a light source. So if there's no light but cold, I guess he would just be stuck. Yeah, he would sort of have this loving behavior where he basically sort of keeps a certain amount of distance and so forth. And so yeah, I see down here that this one is going when I put him on the cold thing. So yeah, I would also be able to, now here I have a yeah, that's the thing when you somehow when you love something too much, you're just scared. That's because it's because I have a minus sign for the sensors here for love, so that basically these motors just go backwards. So yeah, since he's inhibited by the cold, if I activate this cold thing, he's just moving backwards. Yeah, and something else that I discovered from this is that there's basically a class of mechanisms that need something like some internal arousal or something like that, or some intrinsic activity or something, and that is this element here. If I click it, he's going crazy. That's basically a dopamine trip or some amphetamine trip or something, perhaps. So you need this internal activity in order to get mechanisms that work by inhibiting something else. So I kind of internalized this because I wasn't able to make this guy move around without this internal arousal thing. So yeah, and when you move him here, yeah, okay, this. So yeah, that's my current. That was my multisensory vehicle there, and then I skipped all the Breitenberg vehicles at the moment, and I put my attention onto models of the cortex. Because the next thing is that sort of perhaps these kinds of things are a little bit like sort of insect-like brains and intelligences, where basically you have all kinds of labeled lines. Like these things could be genetically built, and yeah, you also see, in principle, this is basically the neurophilosophy, one of the neurophilosophical steps that is sort of at the bottom of what I think is relevant is when you have sensors and motors, or sensors and effectors, it is that you have the connections between these things, and these connections, they are what we can afterwards label the meaning of these. And if you have many elements, like in cortex or something, like when he comes with the threshold devices, logic, and now I make a network of many of these logic gates or something, and then later I have these are feature detectors, these are sort of special shape detectors, more detectors, cellular automata kind of theory things. This one is heavy in theory, this one is the thought pump, which I will talk about later, foresight. That's the idea that you can build a prediction machine and it would be perhaps useful. I'm looking for the so yeah, here. So Breinberg also already imagined that you put together these big elements, like many elements and so forth, and the way that you connect them, you get high dimensional. In this case, 4 dimensions, so slow dimensions. But yeah, like later on, you can imagine that if I have many elements, it's kind of easy. Like you see, it's easy to make a 4-dimensional cube. You simply basically explode the dimension at each node, kind of. Now you can imagine like being a mouse that runs on these wires or something like that, and you would basically move around in 4 dimension. So if I'm an element here, I mean something in sort of a 4-dimensional map now, something, because the meaning is whatever my wires are. That's my idea. That basically from the connections, the meaning is being created, or the meaning is what the connections are. If the meanings are something high dimensional, then that is what the meaning is, something high dimensional. So that would basically be the basic thing for something like cortex, because you have so many elements. Perhaps it's basically making high-dimensional maps of things, situations in the world or something, for instance, and then um, the activity means whatever you are in this high-dimensional space or something. So yeah, then you follow sort of Breitenberg's journey into what is the mind and so forth when he starts talking about what could be the cortex doing with all those neurons and so forth. So we go to a thing where we start thinking about what are theories of cognition and so forth. And to take a step back, I say the problem is that there's a computer that is more or less the real deal, that we don't know at the moment what kind of computation framework and what kind of philosophy of programming we need in order to be able to make these kinds of computers that have the properties of what I would label the brain software. That is that you have what I call a magical interface as a user to the computer that you run on yourself, and you are able to sort of on the fly synthesize explanations and so forth, and you have this property of being able to understand with single examples, and you make analogies and all these kinds of nuanced things that we do, and they kind of easy for us because the computer is so well crafted that it is enabling us to do things that are at the moment out of reach of current machine intelligence approaches. So yeah, what I'm thinking is that this theory of how to do this, I mean, I only know these 4 things, so this is the only thing I sort of can contribute with in some kind of useful way. So I'm going to try to use these 4 things in order to start making explanations of what cognition is, right? What is a computer that is basically an alien spaceship, where if you look back, we will say it was so simple, because it will be an explanation of a process that by itself should be relatively simple, because the genes need to be able to implement some kind of framework in which things like the mind and cognition and so forth sort of are able to be emerge or whatever. Yeah, I call this self-assembled software. It needs to be a software that is programming itself. So the mind must be a programmer that is programming itself, and what are the rules of having this kind of software? What does this mean? And so what kind of computer do you need, and what kind of wiring? How does this relate to the world? What kind of inputs do you need, and what kind of relationship do you have, and so forth. So the only things I know are biology, neuroscience, programming, and computing. So I can't really contribute any physical ideas so much. So I'm gonna stick to these things. Fundamentally, there's something that is missing that many other people are also pointing out, like Hofstadter, for instance, is pointing this out, that if you analyze the thing in terms of a computational layer, you have the problem that there's actually an operating system with a cognitive user inside the system that is so much more relevant for the thing that you want to explain, that the user can just mess with your experiments for fun. If you analyze sort of a memory module of a system, but the user is messing with you and he's just remembering bananas and apples or something just for fun, you basically have a gap that I call a fun gap, because he can have, or she can have simply fun in the system, and the operating system and the user inside the operating system was so important for the analysis of saying what this thing is, that basically analyzing the computational layer is completely inadequate for an explanation. So this is the big picture, yeah, that I want to explain this operating system, this brain software, and that must more or less be implementable by many different kind of computational layers. That is, if a computational layer is the building blocks, then what I'm talking about is the architecture. That is, the theory of buildings is the theory of architecture, not the theory of what building blocks are doing. The building blocks are useful because they give ideas of what kind of things we could be building as architecture and so forth. But it is sort of this organization that is the relevant thing. And since this thing must somehow be biological and self-assembled, I think that this organization is probably perhaps describable in very simple principles. That's what I'm thinking. That I don't make the claim that we understand brain software sort of in terms of cognitive neuroscience, where we kind of say this is attention and this is blah blah and so forth. That we don't make cognitive models, but we explain the same way that the theory of evolution is explaining how all kinds of derived adaptations are able to appear in some fundamental way. That is by saying that what kind of process supports all different kinds of derived detail functions and so forth. So I think that the organization will be something along the same lines of evolutionary theory, that it will be something simple that doesn't mention any of the details. So it doesn't mention any of the, I don't know, memory lookup things or something, but it mentions only the principles of how the software can be created and like how the software can self-assemble. So it's somehow, the problem is that there's a magical interface to an alien computer and it's self-assembled, and as software engineering we sort of start having a little bit of ideas, then we imagine how these figures can interact, then we build a few examples and so forth, and we get a feel for this thing doesn't work at all and so forth and so forth, and you see which things are still missing in your model to be able to express the kinds of things that you need to express. So it's a constant back and forth sort of with highly derived ideas, and here basically as software engineers we are able to do science fiction in the way that Valentino Breitenberg is talking about. This is an exercise in fictional science, or science fiction if you like the better, not for amusement, science fiction in the service of science, or just science if you agree that fiction is part of it, always was and always will be, as long as our brains are only minuscule fragments of the universe, much too small to hold all the facts of the world, but not too idle to speculate about them. I love this because it's putting the imagination at the center of what scientific discovery is, or scientific explanations and so forth. You first need to make conjectures and then see which things work afterwards and so forth. And that's the same thing that software engineering is also doing. We make conjectures, then we try out things a little bit, and then and so forth. So now asking what is this computational layer, and there I go sort of to these neuronal ensembles, and this also has a computing branch sort of theory that is most derived, I think, in the Penty-Canerva model of high-dimensional computing. That is where you simply ask the question, what kind of computer do I get if I don't have 16-bit words or 32-bit words and so forth, but I just make 10,000-bit words. And from this you get something very interesting. And this is sort of that I have a computational framework where I have both ambiguity and I can also model structure and so forth. Because it's easy to implement a bind, or you can figure out how to implement a bind. And you can also represent sort of these association things, and there's it's basically what has recently also been utilized, these properties of high dimensionality in Word2Vec in machine learning. So basically the large language models at the moment, they kind of utilize this high dimensional computing thing a little bit, but they don't have this bind, they don't have a structure approach or something. They only utilize the sort of this context building up thing where things start being associated with each other. That's sort of the ultimate connectionist idea, that from simple associations you would somehow be able to model the mind or something, but it's missing the structure. What Canerva is saying, that we were modeling things in terms of Lisp, and with this thing you have something where you can implement basically a Lisp. You can make the structure and you can make this fuzziness. So the properties of high-dimensional computing, that is that you have a really large space, and these hypervectors then are allowed to be points in this space, and if you look at the single one, then everybody else is very far away, but they're sort of all equally far away, which is already a little bit counterintuitive. You would think that some things have a different distance or something, but because of these mathematical properties, there is basically a Gauss curve where almost all the vectors are roughly the same length apart, if you make a similarity judgment. So yeah, in this high-dimensional computing, you get these properties of high dimensionality. And the first thing is that you have a really large space where the things are almost all the same length apart. And there's only very few points that are close to you. If you plug a point and you remember this, for example, with some auto-associative memory or something, you can basically recover that one from, even if there's a lot of noise and so forth. So this basically is sort of the basis of what I would label a symbolic implementation, or implementation of symbols, and they are points in hyperspace. So whenever you plug one of those points in hyperspace and you remember it somehow in some associative memory, which maybe something like neocortex is implementing, right? Then you can pattern complete back, and you can identify these points. So you will basically be able to remember what you were thinking earlier if you put this into your memory, right? And one of these points here is allowed to basically say, go into the garden, find the bench, look under the bench and find a glass bowl or something, right? These things are allowed to represent, they're not temporarily bounded or anything. Like you allowed to compose via these structure things, so you can represent sequences and so forth, and everything is closed in high dimensional computing. Everything is closed under this hypervector, so that all your operations result in a new hypervector. So it's kind of funny. So if you can pick two symbols, represent the association between these, but it's actually that you just pick another point that is basically similar to both of these in this hyperspace. And so the hypothesis or the assumption maybe is that we can represent a symbolic concept space in terms of hyperspace, that this would be a sufficient model for concept space. And funny, Steve Wolfram was mentioning concepts are particles in concept space, and I think he's basically discovered the same logic here from different angle, where basically if here we have an additional mechanism that is this pattern complete. So basically we say how concept particles could be represented in brain. If brain is doing some high dimensional computing and it also has some auto-associative memory, then it can pattern complete back these symbols, which are now allowed to be particles. I find this kind of cute. Of course, these things are also the basis of memes, cultural memes that jump between brains and so forth. So there's an analysis there that is also an interesting thing. So it's this thing you have a computational idea that there is a hyperspace with points in hyperspace, and these points are basically allowed to represent all kinds of mental content and cognitive content and so forth, that this would be sufficient to represent these things. And they are allowed to make information mixes. That's basically something you get from the pattern complete. If you take, I didn't mention that these things are holographic distributed, encoded. So that means that a single bit is not really important for the data structure, so that you can throw out. That's why you can make the pattern complete in the first place. Different from like integer bit in our computing thing, where like the first bit would be very significant or something like that. Here in a distributed, that's called holographic, because it's the whole data structure that is representing the information. Basically all the bits have the same contribution to what the data structure is. So yeah, this way you yeah, that's kind of that is allowing you to have this pattern. That is allowing you to have this pattern complete, where you get back to the symbols, and this, because you have many elements that contribute to the information, and you can also throw away some of the elements, and you still have the same information content. Now you can throw away a few and mix them in different ways, and this is basically the thing that Breitenberg was also thinking about what Cortex is doing. That Cortex is fundamentally an information, a knowledge mixing machine, that you can say, I have two things and now I represent that these two things are sort of existing together or something like that. And the thing that I think is important is that now from this you have the ability to represent vague data structures. And this is one of the properties that, of course, we don't have so easily in symbolic approaches. But with this approach, we have vague, low detail data structures. And I think that from this, when you represent multiple possibilities, this is one of the things that I sort of require for my theory of cognition, that is below here. Yeah, and with the bind, you you can represent structure, so you can represent role filler pairs. That is what in programming we call this key value pairs. So you have associative data structures, and you can sort of say, I have a container, and there's like something inside the container, but you don't say what is inside the container. So you have a abstract role of the inside of the container or something. Like it's just the key, and the value would be referring to some other data structure again, and so forth. Yeah, and this is the same thing that also has some historical roots and so forth together. But in neuroscience we call it neuronal ensembles, and this is sort of this analysis of what are the neurons doing, sort of on a higher level of analysis, and then you find that you get these synchronous, you get these coherently active neurons. Then, depending on which time window you look. They might be synchronous, but they might also be sort of spread out more. So they are active together, and they would, in the Hebbian idea, they would activate each other. So they would stay active together, for instance. And these are because they're basically, they have the same property that they are made from many sub-elements in a high-dimensional space. They are the same analysis, right? They are being, you can analyze them in the same way that you can analyze high-dimensional computing. So you can see the neuronal ensembles as points in a high-dimensional space that is able to be pattern completed. So yeah, these two things sort of give two branches of understanding, I think. So there's more things to explore, but yeah. So there's this array of amazing neuroscientists that talks about sort of more derived theories of what the neural nets could be doing. And here's an example that I find very joyful. That is, let's say, that is the Günther Palm-Breitenberg thought pump, they called this. That is, let's analyze the cell assemblies a little bit. And let's imagine that the excitability of these things is allowed to be modified dynamically. That's like what they call the threshold device. That would be a separate component in a system. So you have neurons and you have a threshold device. And the threshold device, if it makes the excitability go up and down, what properties do you get? So you can see that there would be a cell assembly, right? They would activate each other. At first, you have, for example, the cell assembly center active because they're sort of in a close relationship with each other. So even if the excitability is low, this one would be active. If you increase the excitability, you would get more neurons being able to be active from this center, and this roughly what they called halo. Is basically that you have cell assemblies that are made from centers and halos. And if you increase the excitability and then you lower it and you increase it and you lower it and so forth, you would basically jump around in these centers, because you would, when you increase it, you would have multiple centers basically here. So in the lowering, you would fall into a new attractor state that was better connected in the system, at least if you do it in a idealized model. So you would basically go from A, boom, then you go up and then down until you basically come to something that doesn't change anymore. So this would be a settled representation now. And this looks a little bit like some thought going from detailed to some new interpretation or something, and sort of finding the settled interpretation or something. So the wider lesson, I think, from this is that you have the neurons, but you can imagine all kinds of devices that mess with the neurons. And from this, basically, you get completely different properties of the system, because you don't limit yourself to the neurons figuring out everything by themselves, but you have something that is using the neurons. It's like you make a neural net, and now you have the ability to mess with the neuronal net in ways that will fundamentally change what the kind of thing is that it's actually doing. So I think that these devices are extremely important idea, so that I'm not limited to modeling neurons, but I can basically think in terms of what are devices around this. And these kinds of things are described in a 1982 book that is an alternative approach to artificial intelligence by Günther Palm, and these things are basically largely ignored at the moment. So there's a lot of growth area in bringing in these associative models and so forth. Here I have an example where you model an attenuation that is simply thinking about what kind of properties you can build into the neurons. Attenuation is that when a neuron is active, it has a lower excitability afterwards. So in other words, the fresh neurons have a higher excitability and a higher chance to be active. So if you imagine the attractor state, it's like whatever is active right now basically gets smoothed out. So whatever is active gets less likely to be active again. And then, if you make a neural area like this, you get these amoebas. That's exactly what Breitenberg was imagining. I think he was saying this, yeah. And this, of course, looks a little bit like sort of this moving activity looks like the traveling waves of contemporary neuroscience. So there's lots of traveling waves in prefrontal cortex, for instance, that are associated with working memory or something. Perhaps the foundation of how this works is because you have a neuronal area with a lot of attenuation for some reason. And perhaps in working memory, now you can make theories about how maybe it is useful that working memory sort of is not, that working memory erases itself very quickly or something like that, but this is just an idea, maybe that's wrong. So now that these are a little bit of ideas of what the computational layer might be, that it's some kind of high-dimensional computing framework with devices and with wiring and so forth, so that basically the world and the brain are in a certain relationship, or the world and the neurons are in a relationship. They are the neurons that sort of represent a high-dimensional space, and there are the cell assemblies as the basic unit of computation, as a basic data type, basically, that represents sort of concepts and sensor data and blah blah and all these things inside the neurons, and that basically there are devices that are able to mess with the neurons. So this is my current idea of what could be the computational layer. So from this, I start thinking now again, how can this start solving the software layer, or how can I analyze this in terms of what the software layer could be. So now comes the crazy part, because now I go into what I think the cognition software of brain might be doing, sort of what brain software could be again, and then we could maybe go back and forth, sort of bouncing between these ideas or something. So the software layer then must somehow encode knowledge. Basically, this must be a design of how the computational and process is being used. I think it's the way that an operating system sort of says what the transistors and what the process is doing. The same way somehow there is a software that says what is the logic, like a program structure. Like these entities might be, for example, files in a file system or something like that. So basically the notion of the file on the file system, or the notion of the desktop, and a mouse click event and these kinds of things, they are the entities of the program, which are like sort of the thing that we think about as programmers. We make a design about what is sort of the causal structure, or what is the explanation in a way. It's hard to put into words. It's just called program. It's in SICP they call it the magic. It's like we invoke the magic of the computer, because there's no good way of explaining this at the moment. And I think this also points a little bit to these deep questions that we still have, that will also be a theory of design and creativity sort of in general and so forth. Because at the moment we make programs, and this is in the mind of the programmer, and this is what programming really is about. The other thing is sort of coding. That is that you have a mental model, and then you go and you make code that basically is an attempt at encoding this mental model. So these things are always sort of approximations to what is actually happening, and this is somehow sort of what software is. Software is sort of this this golden part or yellow part or whatever, and the process, I think, is what I make green, and the code is what I make blue. So you have some kind of interpreter that is basically saying, I take code and I make process out of this code. So this is the so-called execution of program code. And then this must somehow bottom out. So it must be that each process must be decomposable into sub-processes until you have something that is so easy to express in terms of some kind of circuit or something, so that physical reality can take over this task. So that's sort of my theory of computing at the moment, from a high level. And the software layer is so much more important about what is the computational layer doing, that I call this the fun gap again. Just that you need to understand the software in terms in order to understand what this whole system is doing in the first place. And this is something designed, so there is somehow knowledge in this thing, and this, there is no programmer that can make this. I think so, or it's self-evident, I think. So basically, we must self-assemble. The software must self-assemble before the programmer, and this would basically require creating knowledge without somebody that is able to make the knowledge. And there's one theory that we have that is able to do this, and that is the theory of evolution. So it's actually sort of the conventional view that we try to use a theory of evolution to sort of say what brain software might be doing, or how brain software can be created. And what you don't do you cannot explain life in terms of sort of taking many niche data or something, then make some kind of random biochemistry or something, and then start seeing some cells that do certain like biochemistry things that look like, oh, there's sugar and ATP or something like that. That's not a theory of life. And I think the same way we cannot relate inputs and outputs and have a black box and statistical methods and so forth, and think that this would ever be anything close to a theory of cognition or a theory of creativity or something like that. So yeah, let's just jump ahead. I think that let's just take the theory of evolution kind of seriously, say that there's in general something like variation of things, and then there's a selection of things, and this sort of mirrors the Popperian thing of there's conjecture and then refutation. This is fundamentally a philosophical paradigm as well, because now we are saying that the ideas must somehow be there first, and then there must be a process of criticism that basically selects which ideas are allowed to survive. So if basically the brain software is implementing milieu for sort of ideas to exist, then if this would be the function, then we can label an element, the memetic engine, that would basically try out many variations, and this is allowed to be computational. It doesn't need to, in the same way that evolution needs to try out many things and then sort of see which variations work in copy numbers and so forth. It's allowed to have a computational model that makes many things in parallel and then selects from these parallel possibility things. And that's why I emphasize this idea that in high-dimensional computing we can have vague things that represent many things at once, and as well this thought pump idea, that is an idea of a parallel search algorithm, and that would sort of this would kind of say a little bit how you can have something like natural selection, but you have it so much more efficient, so much faster, because this thing is parallel. So I only need 2 time steps, and I find sort of a new, well-connected well, I would label it interpretation then. So you move from interpretation to interpretation in a parallel thing, so that you don't need to worry that much about um, how this variation and selection is played out evolutionary or something is allowed to be a very computational thing, and this of course is sort of part of the open question marks of how you model something like this. But and my general idea would be something like that you have a lot of things possible, and that then given the context you find sort of an interpretation that fits with the things that are possible a little bit or something. So that's kind of my idea at the moment. And yeah, if we have neuronal ensembles, then we can implement this randomness and this probability thing a little bit with simply intrinsic random firing rate and neuron failure rate as well. So neuron failure rate is a misnomer because it's not that the neurons fail to fire, which is 40% of the time or something. It's basically a deep mystery of neuroscience. Why? But you see, you can explain it with assembly shift. That is that if I have a little bit of the opportunity to change the current interpretation into a new one, I'm kind of representing sort of a cloud of possibilities for each data point. Basically, I'm actually representing sort of the cloud of counterfactual possibilities, I think, so that each of these high-dimensional symbols in the end is basically sort of a point, but it's also sort of the possible continuations of the point. And it's kind of reflected in this assembly with its halo, where there might be different connections here, right, with different kinds of overlaps again. So it's like I can imagine that I open the drawer and then I see in the drawer I either see paper or something, or I see some toys or something like that, and then depending on my expectation I would fall into one of these interpretations or whatever. Okay, wait, I cut this and I say basically, I think if you look in the Necker cube or something like this dress here, that basically these possibilities sort of would all be represented a little bit, and then you would fall into one of your interpretations. Yeah, and these are now allowed to be the memes. So we have a high-dimensional computing framework, and the things are either stable or they're not stable. And this is also reflected in the logic of how the activities actually, it's hard for the activity to actually survive in the neuronal network, because the excitability properties, the electrophysiological properties and so forth are actually in a way where the activity needs to sort of struggle for survival. This also makes sense, because otherwise you would have epilepsy. If you have a recurrent neural net, you have a constant struggle against epilepsy, basically. So there's all kinds of forms of epilepsy, because there's all kinds of inhibitory mechanisms that keep the activity in check, which must be basically one of the main things that these devices are doing in the first place, is making sure that the neurons don't basically are selfish memes in my conceptualization now, and basically say I'm gonna activate everybody and then I'm gonna be active, right? Conversely, the meme that tries to inhibit everybody, or the meme that is not activating everybody, or is activating nobody, this meme is simply dying out immediately. Because if I'm not activating anybody, then I will also not cause the computer to reinstantiate me, I think. So what do the memes want to do? So these memes, I label them, they are the high-dimensional data structures in the software framework now. And perhaps this is making a virtual simulated world where there's basically sort of animals now basically being computationally simulated. And then this sort of becomes a biological plane by itself again. This sort of knits it all together, sort of with technology and life and so forth. And that goes into thoughts as well, so that I would then now say that the thoughts are alive too, that the point of the brain computational layer is to create a new plane of biological, of something that has more of a biological logic again. So it's kind of like that you had, you understood biology, then you saw that the brain is a computer, you thought that you need to explain it in terms of computation, but then there is now the thing that this computation is implementing a new thing that is actually now understood in terms of biology. I find this is quite beautiful. I think it's very poetic, and sort of it says that life and thinking or whatever, like that these things are understood in the same unifying fundamental theory of knowledge and of how systems are stable and so forth. It's also, I think, a very cybernetic thing. That's sort of all about how systems are stable in the world, and this is basically implementing a computational framework that says I allow for information to be stable, and perhaps this is basically what you need in order to create a software that is running on a computer by itself. So let me make this case maybe, or let me show you my current ideas. I don't know. So if you have memes, they are replicators when they are able to cause something in the world that modifies the environment in which they exist in a way that after some time they will be reinstantiated. So it's a little bit different from something like RNA or whatever that is able to copy itself, and it's also different from genes that have a copy mechanism and so forth, where they basically can faithfully reproduce. But this one can only faithfully reproduce in the approximation of how good the pattern complete works of the thing, which I'm basically saying that this would be the basic thing, that the high dimensional computing allows the pattern complete, and that these things are allowed to be the memes that are being pattern completed. And this basically looks like, if this is the function of brain, then it would make a pattern complete implementation. So sort of you can analyze brain in terms of these questions, and I think that you will get answers that are interesting. So yeah, the replicator basically would pattern complete here. So the replicator would sort of be in a possible state a little bit, and then once the computational framework is in a state that is similar to what would pattern complete it, it will pattern complete again. So this meme would basically replicate across neuron time steps, or across time steps in the computational framework. So now, of course, these things are encoding how they're encoding their meaning in terms of what they are connected to. It only works in sort of a system that is connected to the world and so forth, that has meaning by virtue of what the connections are in the end. So these things basically, and when you analyze them, you ask sort of what are the possible meanings in this network, and sort of what could be the extent of the neuron of this data structure sort of what kinds of things can they basically represent. And this is what data structure and function is. Also labeled as the data ad hoc epistemology, because it kind of says you're stable in the brain by representing some kind of knowledge that is basically stable in this computational framework. And if there's a lot of activity from the sensors, driven from the sensors somehow, or you can criticize your alternatives in terms of the sensors in some way, which is like open questions, then you would say that whoever is basically representing something that fits with the sensors, that guy is basically active and is allowed to be stable. If they are representing something that is true, even though that the sensors change, you're representing something more abstract, and now you are able to replicate more often, or you're just a better meme. If you represent abstract notions of the world, you are a better meme then. Now, there's basically, if you take Maurice Sherman seriously, you think about the wiring of these things, you come to a view where the data structures that span cortex, that's a little bit of hypothesis, but I think it would make sense that basically the ensembles, they try to spread as much as they can because they want to find support from somewhere else in the system, because then they are sort of in a loop that activates each other. So they will try to span as much as they can. All real estate of neurons basically is saturated by memes if they can, simply because the ones that don't have the right connections to spread, they will just not be around. Now with this Maurice Sherman wiring thalamic idea, you get the idea that in order to spread to the higher area, I have to output some kind of motor output, and this is now able to be interpreted, I think, in the next area. So I think that this is the story of what it means to stretch cortical areas, is that you output an affordance at the lower area, so to say, or the more sensory one, and this is feed forward. That's empirical by Sherman, that basically the cortical thalamic connections, they go from sensory to higher in a feed forward way, and this is actually required for the activity here. This is what they call driving inputs. So the driving inputs all come from thalamus, and so in order to actually have the effect of having the chance of having a higher friend, so to say, that basically activates you back. So that is, if you are a blue sensor here and you have a higher friend up, this says that there's a blue dress here, or it's white for you, I don't know, then the only chance you have is by outputting motor data. So this is something that I call the memetic game of the circuits, because the way the circuits are laid out, this tells you what kind of memes you have in the system. This is like very important, I think, for this type of analysis, that basically says what kinds of meanings are possible, and also what are the strategies that the memes need to do in the first place, and these kinds of things. So in this case, they need to output motor data, but this is sort of a tension. This is a conflict for the meme, because if I'm representing blue, right? If I say, yeah, your fovea is blue right now, right? This is sensor data that you look at something blue, then I have the problem that if I output, let's say, eye movement data, because I'm connected to superior colliculus and motor targets that move my eyes now. If I output this motor data and I move somewhere else in the visual scene, then I'm less active because this is blue. So I think that the memes are selected for. There is a memetic driver to output the maximal motor output that they can, that still keeps them active. So they need to output motor data that basically would move your eyes only on the spots that are blue. In this way, on the higher layer, you can interpret this as the extent of the object. And I think the same way, basically, you would have these segments of affordance and then of interpretation in the next layer and so forth. And that would be, for example, the eye position would be encoded by the eye motor movement of how to move to where you would look at me, basically. The data structure would tell the system how you can look there, and that would basically encode where in the new interpretation of the thing, right? It would sort of go in this flip-flop between motor data that basically says what the affordances are, and then interpretation of the motor data again, and so forth. So it would say sort of, you can grab me and then it will feel like that or something like that. If this basically sort of is implicated and bound in some ways to sort of these motor things together with like possible data things. So they're all counterfactual data structures in a way, because they sort of say, if you look here, then you will see this color. And by encoding this counterfactual, you are actually encoding from a different perspective. You're actually encoding something like color, filled-in color of a visual scene object, something. So yeah, it would basically be a requirement a little bit for these things to be able to bind different aspects of sensor data and so forth, and motor data on the fly, and they need to, this needs to be separatable, this needs to be modular, right? I want to be able to say, yeah, here's a line, so move your eyes in this left right way, and then you will stay on my turf, basically. But you want to have this decoupled from the color, for instance, so that these things are allowed to be put together. That's would be a basic requirement of compositionality in this way. So this would be one of the things I would be looking for in my models and so forth, basically. So then you have so much cortex, but only so little sensory cortex, which actually a little bit of a mystery, or because what is perception if not sort of representing the sensor data or something? And I would say that if we analyze this in terms of ensembles, they are stretching this whole cortex basically from front to back. You would have basically an inverted iceberg thing, where most of the stuff that our perception is about is the stuff that we don't see, and the stuff that basically sort of says what we expect in what kind of situation. And these are basically the ideas that are completely decoupled from the sensors. And I think this is sort of a neurophilosophical paradigm as well, to say that the ideas are there on their own in a way. And so perception is the stuff that you don't see, funnily enough. The same way that science is about the stuff that we don't see, that perception is about the stuff, about sort of our expectation structures that say that there's an object and it's moving or something, and here I have the idea that there's a glass, and when it falls there would be water spilling or something, but you don't see the water spilling, it's only a counterfactual. But from having this idea of this counterfactual, you can build an expectation structure of what you would see if you look at this glass or something. And that would, I think, be all this part that basically is saying what the ideas are without actually... They would be able to stretch into the sensor level, and by doing so they would create what we label perception, I think. So if you look at this, you basically have the idea that there's a dress, and the idea is basically bigger than your sensor data here. The same thing with phantom pain, that points to the same logic, that there's basically stuff active somehow that is not the stuff from the sensors. And it's kind of an important idea that the ideas are sort of, they are on their own, and that the sensors are maybe only sort of a resource for the ideas to be stable in some kind of game, where perhaps they use the sensors to say they are more relevant than some other idea or something, but they are open questions in this kind of thing. So the ideas are made from affordances and from sort of sensor data, or some kind of perception interpretation thing or something like that. And they all basically are buttons, I think. That's what they do. I think that they represent how to be more relevant in the in this computational framework. So all the ideas sort of say how they can be used, I think. And that is sort of easy if you think in terms of visual scene objects. They would all output how you can look at them. And by doing so, they would basically encode their position. And these commitment structures would be sort of, I would hypothesize these must exist somehow. They basically kind of select from all the affordances that are sort of possible, which ones are basically being executed somehow. And then maybe the story of prefrontal and so forth is that basically it's representing different kinds of affordances that allow this thing to be represented in something like working memory, or something like I can be thought, or I can be mentally navigated to, and so forth. So this way I basically, I think that the analysis of sort of internal cognitive moves and blah blah and so forth, it's all the same analysis. It's that there are affordances. It's just that these are a little bit more derived in the meaning levels of this cognitive system. I skipped this for the moment, whatever. Okay, so the memes would be sort of their own little animals. They basically have causal power, and they basically encode knowledge of how to survive in the system. So they're more like animals. It's a biological system. That's my idea. So if they basically encode this knowledge, that's also what is called adaptation. Given a niche, you are a replicator if you have adaptation. That means that you encode the right kind of knowledge that will cause you to be replicated. That also means that, now we can analyze this in terms of abstract replicator theory. So you get to something like selfish gene and extended phenotype, which are now sort of relevant analysis levels for these kinds of computational software entities. Right? They play games, they cooperate, they are harmonic, and they are strategic. And strategic is that you say that it's okay for me to not be on for a while if in the long run I'm on more. So you can basically say, if I'm a banana meme, if I'm activated by bananas, then I can play a game where I actually activate an apple in turn. It might even be good for me to sometimes move the system into a state where the apple is active instead of me, so that in the long run I'm basically more stable in the system. And this of course is allowed to become arbitrarily complicated, and because these ensembles are allowed to represent abstract templates as well, for instance. So if they have basically little niches here, it's kind of the same idea as this. You would be able to represent roles and fillers in this way, and you would say that I'm a container, for example. I can contain something, but you don't specify it. You leave it vague, basically. You say that there's a role that is the internal of the container, but you don't say what kind of thing is inside the container. So you become an abstract tiny situation in Hofstadter's terms. That's also called a frame, or a framework with roles and fillers. And these things are sort of allowed to compose. So if I'm allowed to basically think in terms of one element is made from sub-elements. This is then also the topic of neuronal syntax, that is about, if you say this is a high-dimensional data structure, an atomic data structure, then you have an atomic ensemble, and now you have the means of combination of how these atomic ensembles are arranged, and that would be a little bit like the letters or the notes, and then you would have a syntax or the music rules and so forth that would be able to compose them into some composite data structure then That's the lists and the maps and so forth that we have in programming. But the cute thing is that if I look at a composite high-dimensional data structure, first of all, in high-dimensional computing, they're actually closed under the hypervector. And in neuronal ensemble theory, you can always increase the time window that you look at, and if you make a reader, you actually can treat a bigger ensemble, sort of a composite ensemble, as a single one. So this one basically would represent the composite one. So in terms of high-dimensional computing, this one would be a hypervector by itself again, a hyperpoint by itself again. So this one would have its own logic again. So this is allowed to be a meme by itself. This one is basically activating sort of the start here a little bit. Let's say that this one is the alphabet, and the alphabet is activating the A a little bit, and it's kind of activating the sound of the tune of A B C D E that you sing, right? Then this one is allowed to represent the alphabet, but it's also sort of allowed to it's its own meme, and it's its own meme allowed to point to a composite, for instance. So the cool thing is that basically we get the means of abstraction and the means the means of composition, of combination, the means of combination. We get them both sort of in the same with the same data type, I think. So this is technically quite sweet, because now I basically can have the equivalent of procedures, and I can think and encode them in the same kind of living meme data structure again. So now basically the procedures and the little situations that basically encode abstract things like the container, that one is also a living meme again. It's the same thing. It's just exactly the same thing. So these things actually then start having drivers for abstraction. That is, if let's say I'm activated by sort of this sensor data, and basically this is now my high-dimensional representation, then I actually have memetic drivers to become or to find a subset or whatever, to with random variation in some way basically start representing an abstract banana symbol. And it goes further, that once you start having sort of higher strategic memes, they will in turn sort of have an agenda for their lower memes. So for this, I'm imagining sort of a wizard in this computational virtual simulated world. If the wizard basically finds some gems or crafts gems or something, and he's basically activated by the activity. If he finds a nice gem and he sees that this gem is sort of activated by other things like the word banana, then he will basically craft this gem, and then he will in turn use his buttons that he has to the cognitive machine in order to say, here, speak the word banana or something, because then my gem is glowing. And how do you get these crazy advanced memes? This is that now we get into the logic of what software is, and that is that I think the analysis of software this is still a developing field. I think this almost doesn't exist. It's the philosophy of programming that is underdeveloped, but there are somehow these systems of expression that are allowed to be put together, and that you're also allowed to make new ones and sort of point to collections of ones. So that's abstraction and compositionality. These things are sort of building blocks that allow you to, in some kind of universal way or very general way, express a space of things to be expressed. For example, explanation structures that basically are stable in a virtual simulated world or something like that. And these things basically, I think, would create this logic would basically be memetic drivers to separate the memes a little bit, to have one layer that is more the producer layer and one layer that is more the user layer. Yeah, it's kind of a hypothesis about the memetics of software, of self-assembling software a little bit. I would say that this would always be a memetic driver of self-assembling software. And now you would have a computing framework that is made from memes that try to be used for software memes, like good buttons and good things to put together, like good building blocks and so forth. And you have sort of competent memes that use the computer in order to be stable, to play extremely strategic games, to basically have a very far cognitive light cone. That's what Michael Levin is saying. There's an agent can sort of, how far can they look into the future, but this also means sort of how far can they move away from their actual goal. So this is like when you solve a Rubik's Cube, you need to break the pattern. And this is basically sort of the story that I see for these highly strategic, competent memes that basically start using the computer that they run on to influence this in the right way, so that they play a game where they are active in sort of very long future after further future time steps, kind of. So this would be A prime, because it's never actually A, because if there's time in between, you never actually ignite the same symbol again. I think this is a property of just of electrophysiology. You don't get the same. It would basically be a Boltzmann brain, but this is just as an aside. So yeah, once you start having these very competent strategic memes with like long futures, this looks a little bit like a survival software implementation already. That basically, if I start having sort of memes that have the right causal structure, that basically are sort of made from software here, it's quite wild, but hey. If they are able to play a game that says that I need to, for example, keep the body alive because I want to be active tomorrow as well. So I know that I need to go and eat because otherwise I wouldn't be living anymore and so forth. So these things you can then later label the self or personalities or something. Like these are things that play large games, and they're sort of made from they are kind of using large parts of the computer in order to achieve their goals. And that of course looks a little bit like then at the highest layers of this thing. This looks a little bit like what we label our self and so forth. So yeah, I think that there are basically systems of expression that sort of go up in this way, and this way you have software. And I think that we basically know that somehow some layers of abstraction must, like this idea must be true, because otherwise we wouldn't be this cognitive user that sort of is like removed from all these details. So I think this is basically a basic requirement for brain software in the first place anyway. So we might as well require it in our explanation, or we actually should require it in our explanation. So it's kind of sweet afterwards. Yeah. So I'm requiring these user strategic memes in the explanation of this whole thing. And now you have this kind of stuff. So the moment that I have sort of a personality habit trait that basically finds new words in the world, and it basically is rooting for the words now and saying, I keep this in working memory and so forth, and I'm gonna say this word because I like it and so forth, and blah blah. I basically become a larger strategic meme that basically finds many words and then is sort of activated by these words, because I'm the process that is saying I'm gonna find words in the world and so forth. And this is sort of what I would say that is part of the process that makes children acquire languages, that they have a language acquiring process that is a meme by itself that basically says, I'm so highly abstract, I can, or I have, I'm so high in sort of hierarchies of how I use the computer that I can basically do with confidence, swag, influence the computer in ways that will make me dominant in the memetic jungle. So these systems of expression, they're the same thing as technology. I think they are basically this life and technology, that these things are sort of like somehow the same kind of thing if you analyze it from a fundamental perspective somehow. And basically this thing is a technology implementation thing. So that's how basically the memes are allowed to build up to something like cognitive software that I would say is sort of a high technology achievement or something that is basically yeah, I'm not sure. It's made from self-evolving technology. So some kind of it is a technology where basically you have buttons to the things that you do, and this is what I label the magical interfaces. That is our cognitive software is so good that we are so removed from the details. We basically just move our muscles in ways that we don't understand ourselves, and this is good. This is basically what a good interface is, that you have absolutely no idea of the details. That is also what Dan Dennett was labeling the user illusion, was that there's abstraction things, so the details are removed. I think that the term user illusion is a mistake because it comes across like that means that this doesn't exist or something. But it's the exact opposite is true. It is existing, and it's actually the most important aspect of how to explain this thing in the first place. Asking how do magical interfaces work. So that's why I call them magical interfaces, because they are real just as any magic is indistinguishable from technology given the right knowledge. That's David Deutsch and Arthur Clarke. Any sufficiently advanced technology is indistinguishable from magic. That if you would be running on a simulated virtual world and you would see magic, it would be able to be implemented by technology, but you would think that it's magic. And afterwards, we will be able to say how it's technology. Basically, from everything that is possible, there are things that are simply that look like magic, but because they are possible, we are able to explain them. So it will be indistinguishable from technology given the right knowledge. I find this beautiful. So once you have sort of user level entities, I'm imagining sort of competent wizards that are memetically selected, right? This is sort of the lesson of Darwin is that these things are highly derived, so they're agents, they are competent, they have competent drivers because they say, I can have a large cognitive light cone, I can be a good agent, so basically I'm using the technology at hand in the right ways so that I stay stable and so forth. So there are on one hand the competency drivers, and on the other hand there's sort of these abstraction drivers to make the software better software. Because it's the connection between these two things that is most stable. So you have kind of the software memes that basically make up the simulated virtual world that then becomes something like the Matrix, that says I'm basically magical, like I'm representing things to you that you can use in order to explain the world and so forth. Or I'm a nice button so that you can bring a banana to mind. But you don't know how you bring a banana to mind. It's a magical button, basically. It sort of knows how to bring itself to mind. So these things become very, very useful. So they have useful drivers and they become harmonic because if you can put the building blocks together in nice ways, then this thing is more powerful, more useful. So these things have these memetic drivers to become expressive languages. and the user level entities have the memetic driver to become competent and use with confidence and swag, with artistic swag, the computer that they run on. So that's sort of my idea. And now, how does this thing then basically become magical? Let's imagine that this is simulating a matrix, and you have sort of these wizards in the matrix that are basically compared, because you have many alternative wizards. You have not only one neo, but you have sort of many neos, and some of them don't attempt to stop the bullets, but some of them they do attempt to stop the bullets, and some of them I don't know, they don't exist or something like that. So there's all these possible things in this virtual simulated world that maybe you can call matrix possible, and then there's matrix stable, which is sort of the subset where Neo was actually stopping the bullet, for example, because for some reason this was important in his agency as a stable meme, right? So if he's able to use the computer, he will do so, and the versions of Neo that do this without caring about the system that they run on, the versions of Neo that basically do this fast and competent and basically just imagine that it would work, like they just pretend it would work, these versions are the best versions. So basically you are a good action hero wizard in this world, a user level entity, when you simply pretend that the thing that you run on is magic. And this would work in a natural selection paradigm if I basically have a memetic engine that creates a matrix, and I basically try random things like manifesting a banana in the virtual simulated world, right? Now, if the wizard is doing a random thing like saying banana, and at the same time the matrix is instantiating a banana in the spot, just because it was trying it out, just because many things were possible, then this wizard was competent to manifest bananas. And if this thing is now stable in this system, you will actually sort of make this software system of this wizard being able to manifest a banana stable. So yeah, he's basically able to sort of craft his own technology using the magic of this matrix by simply pretending that magic would be true, and if the matrix is basically trying out all the kinds of things, basically implementing magic, and afterwards these highly improbable virtual worlds are basically selected, right? These are the ones that are stable. Then you get the holy overlap of optimism and competence. That is that the wizard can be optimistic and can simply pretend that he can manifest bananas, and the virtual simulated world can simply try out manifesting bananas, and usually it doesn't work, or usually it doesn't do anything. But in the overlap, it would then basically implement the magic so that it knows that if this is the context, I'm gonna manifest bananas. So basically, you start having memes that sort of represent the notion that you can press a button and I will create bananas in this virtual world. Then, so yeah, because everything is made out of activation flow in the end, and if you select activation flows, you will get these activation flows that overlap in this way. I think this is more or less true. Kind of just one idea. But yeah, it says sort of how we have a cognitive interface to a virtual simulated world, where we are users inside this thing, but we also don't know how it works. And yeah, in the end, the analysis of what cognition software is, in a way, is, I think, actually the analysis of what realities are and what virtual realities are. So this is kind of a funny twist that at the bottom you find that in order to explain consciousness or something, in the end, you actually need to explain reality. Um, I think this is what this says basically. Is the neuronal ensembles, and in some ways this actually sort of starts with magnetism, where we had a physical process that was not understood, and that was Ernst Ising that came up with the model of describing magnetism, and this is the I think discovery of emergence in physics basically. So emergence is a physical term. It's like you don't hear it so much in biology, because in biology we simply talk about the function and structure um, of structures and organisms and so forth. So it's a little bit of an import from physics to even mention emergence. But yeah, so this model says that if you have atoms with spins and so forth, then you describe, like, this is quite elegant, all the interactions, and you take the sum and then you make a negative and call this energy. And then you find that the system will fall into the lowest energy state. That's the same thing as being stable. So energy is the opposite of stableness or something like this, I guess. So whenever you hear energy in the context of neural nets, it's basically this stableness. So yeah, I love Raphael Juste. He's giving sort of nice overview and history and so forth, and is basically doing electrophys on the neuronal ensembles. They have a great future in in neuroscience. I think it's strange that it's a little bit niche neuroscience. I think that everybody should just talk about the neural ensembles and to move forward from there. But yeah. So this is relevant because so we had basically early neuroscientists. First we had something called a neuron doctrine, or that still that still exists. That is that you think that the functional unit of cortex is a neuron, and this was sort of important because they initially they thought that brain is perhaps made from something else than cells, but it was an important step in biology to say that it's also made from cells again and so forth. So this was the root of this, where Kayal and Golshi were sort of making these visualizations with microscopy to say that these things are cells, and then you can analyze it in terms of cellular structures, and somehow the wiring must somehow create this whole mentality kind of psychology and so forth. But as Just is saying, it's like looking at a pixel of a screen, but there should be something like an image. And that was that early Turing also had this in his drawings actually, that these nodes, if they go back and forth, you have sort of a state that is stable. Once you go into one state, you have your machine will represent this state from then on, and this is important because now you have the ability to go into this state independently of the sensors. And that was also what Laurent Denou was talking about, and he called this the reverberating chains. Yes, Laurent. And Hebb called them cell assemblies. Yeah, so Lorente was the first guy, talking about if you have loops in these things. That's like nowadays a little bit out of favor because these feed-forward neural nets work so well. So you think why have recurrent neural nets or something like that? But if you have loops, then you are able to have activity that is independent of the sensors or something. And I think this is the basic step. Raphael Juste also says this, that basically allows you to represent your sensor data without the sensors. And this is sort of the basic thing, I think, that is the doorway into a theory of mentality. So that would be that you generate basically expectations about what the sensors could be and so forth. And this looks a little bit like now I'm able to put together different kinds of sensor data, and I can basically represent things in a virtual simulated way. So this I think is basically the thing that we afterwards can label mentality then. So these things was Donald Hebb, and basically his Hebbian theory book. That is that this is the same thing. This would be ensemble. He called them cell assemblies. Then imagine you have a neuron being active here, and then you go, and now this neuron is active, and so forth. Then 2 and 3 and 4. So this neuron was active in 1 and 2, 1 and 4, kind of, and so forth. So you basically build a little bit of a network of self-activating things, and this would be he called them assembly. And now if you have multiple of these, so let's say that you have A that is sort of going a little bit, and you have B. Now his idea was this Hebbian plasticity, that if you have some kind of association rule that if B is active and A was active just right now, then we strengthen the synapses, and this is this fire together Hebbian rule. Is basically emphasizing sort of causality structure, because if you have if you have many arrows going from A to B but not the other way around, then you kind of say that B follows A. But if you have many arrows that go between A and B, you kind of say that these two things are causing each other, so they're sort of just associated or something. So you can basically have fundamentally these two ideas there that Breitenberg in his book called Ergotrix and Memotrix as well, because he was mainly inspired by Hebb. So he also called his theory the cell assemblies, but it's all the same thing. So yeah, this emphasizes the causality structures, that basically once you would build representations of the world in your cortex, and you make these causality connections via something like Hebbian plasticity, you would then basically be able to predict, for example, sort of the future, that if I'm in one state, then I can sort of say what are the continuations of this state, and that's all independent of the sensors then afterwards, and that looks a little bit like mentality, right? So it's basically emphasizing this virtual world of I'm predicting things in causal ways or something like that, and that is Breitenberg calls this a neurophilosophical paradigm. Yeah, I think it's a fragment of a philosophical paradigm. And then you have Hopfield that takes this magnetism equation and basically says, what if you have a neural net where everything is connected with everything else, sort of as an idealized abstraction, and you describe it with this physical emergence theory that we already have for magnetism, And so this is where this energy notion comes into play. And this is where if you have a neural net like this Hopfield net, and you have something like Hebbian plasticity, you can create by presenting this multiple times. You basically stretch down, you shape the landscape of this thing. This is called the attractor landscape, because these bottoms here are called attractors. And this is basically an autoassociative memory. That is that this kind of stuff goes in and it's pattern completed into this. So with an autoassociative memory, you can associate the pattern with itself, with sort of like variations of itself a little bit. That's like when you are at the edge here and you fall down. There's basically this basin or this attractor, this region where the attractor basically has the power of pattern completing anything back to one of its stored memory states, something. So that's very like that's cool, because it's sort of a very mathematical theory that kind of says sort of how you can have a pattern complete in just from some neurons, right? Like this statistics, and you basically see these if you look at the neurons firing in time, then you see that these neurons are, for example, firing together. So if you plot them like this, you get these columns, but this sort of they're spread out or whatever. So this anatomy of these ensembles is one of the things that I'm interested in. Yeah, because what kind of neurons, basically, what kind of network do I want to make, so that sort of what is the shape of these? And yeah, then they went further and they created these. They were able to create these ensembles artificially, which they call artificial ensemble. So that looks a little bit like Hebbian things, like you activate some things together and now they stay. And they were able to take an existing ensemble and activate single neurons, and then boom, you get the whole thing back, right? So the ensemble theory is a little bit that you sort of have fire. It's how does the spread and so forth. Okay, I guess the analogy just breaks down. But the thing is that the forest is sort of a wet forest. It's actually hard for the activity to spread, and that is what Moshes Abeles is emphasizing, that the environment for this activity to exist is actually sort of hostile to activity. So that only synchronous neurons, they sort of need to work together in order to propagate, and this is what is called a synfire chain, that you would have populations of synchronous neurons that basically manage to jump to the next place or something, and then of course it could go back and forth again or something. You would just represent sort of these two things being active together, or it could be sort of in sequences or something. Then you would perhaps represent the notion that these things are sort of in a sequence, or causalities or something like that. And so these ensembles, because they are able to pattern complete back from sort of a vague state, we might call them the internal units of perception. I think this is correct. Yeah, so I think this is a theory of mentality, basically.